Hi all, let's see the next topic of multiprocessors, interconnection structures. So in today's lecture, we are going to discuss about an introduction to what is an interconnection structure and what are the different types of interconnection structures available. So coming to a introduction, as we know, the multiprocessor system consists of multiple processors present within a single computer system in order to improve the performance of your system. So that parallel processing is possible when you have multiple processors present in a single computer system. So a multiprocessor system consists of set of components like CPU, memory, input output processors, and all these components they communicate with each other. And the collection of paths that connects these various components is said to be called as the interconnection structures. So in order to accommodate the communication among multiple components that are present in the system, we need to have some set of paths established between them so that the communication is possible. So that connections is said to be called as interconnection structures. So there are five ways in which we can interconnect different types of CPUs. One is time shared common bus, multi-port memory, crossbar switch, multi-stage switching network, and hypercube system. So coming to the first type of an interconnection structure, which is a time shared common bus. So here, as the name implies, common bus. Here, all the CPUs are connected to the memory with the help of a common bus, single common bus. So the memory, so that the memory access is shared and uniform. So here, if you look at this diagram, you have a single memory unit where all the different types of processors. If you observe here, there are two types of processors. One is the normal CPUs and other is the IOPs, input output processors. So input CPUs are responsible. CPUs contains the ALU related. They are responsible for executing the ALU related instructions, whereas IOPs, input output processors, are responsible to execute the input output related instructions. So all these processor, different types of processors are connected to the memory unit through a single common bus. So the name implies it is a time shared common bus, which means that the time is shared between all the CPUs that are connected to the particular bus. So if a processor can use the bus only whenever the bus is free, which means that only one processor at a time is allowed to access the bus. So say for example, if the CPU one wants to access the memory unit, then all the remaining processors, CPU2, CPU3, IOP1, IOP2, all these processors have to go into an idle state. And similarly, if CPU1 wants to communicate with CPU3, the CPU1 only can access the bus in order to communicate with CPU3. Whereas the remaining processors, CPU2, IOP1 and IOP2, they have to go into an idle state. So it means that only one processor can use the bus whenever the bus is free. So when one processor is using the bus, all the remaining processors that are connected to the bus have to go into an idle state. So this is a interconnection structure where you have multiple CPUs connected to a each CPU has its own local bus and they are connected also to the system bus in order to access a common shared memory. So if you see here, this is one CPU which has its own bus controller, CPU, input output processor, and a local memory. This is CPU2 which has the same bus controller, CPU, IOP, and local memory. This is other CPU. So all these three CPUs, with the help of a bus controller, they are going to connect to the system bus in order to access the common shared memory which is accessible by all the processors which are connected to the system. So each local bus may be connected to a CPU, an IOP or any combination of processors. A system bus controller links each local bus to a common system bus. So the controller links this particular local bus to the system bus. And the IO devices connected to the local IOP as well as the local memory are available with the local processor. So the memory connected to the common bus system, it is being shared by all processors. At a one point of time, only one CPU can access the bus in order to communicate with either the common shared memory or in order to communicate with any other processor which is connected to the system. So coming to the disadvantages of a time shared common bus, only one processor can communicate with the memory or another processor at a given point of time. So as a consequence, what happens? The total overall transfer rate within the system is limited because there is only way for one processor to access the common bus path. So transfer rate cannot be high because only one processor can communicate at a time. In order to overcome this a disadvantage of a time shared common bus, we go for the next type of interconnection structure which is called as a multi-port memory. So multi-port memory, it employs separate buses between each memory module and each CPU. So here we have multiple buses and multiple memory modules. So for each and every CPU that is present in the system, we have one bus present. It has its own bus, and there are the memory is divided into multiple modules, and each CPU is connected to each module. If you look at this diagram, you have four processors present in your system, and the shared memory is divided into four modules: mm1, mm2, mm3, and mm4. And all these CPUs have their own bus, so own bus, and each CPU is connected to each module with the help of a multi-port memory. Multi-port. So this is a multi-port memory. It can be connected to all the CPUs. CPU1, CPU2, CPU3, and CPU4. So CPU2 can access the multi-port memory MM1 with the help of this particular port. So each memory module has four ports connected to all the four CPUs that are present in the system. And this this particular bus is the bus which is connected to each CPU. It has address line, data line, and control line. So if at all a CPU wants to communicate with any particular module, memory module, say CPU one wants to communicate to with memory module one, it places its address of the memory module onto the address bus, and the corresponding data that has to be transferred is placed onto the data bus. And the control line specifies what type of operation takes place, whether it is a read operation or a write operation. So if you consider the advantage of this particular approach, the data transfer rate is very high. All CPUs can access the same memory, but no two CPUs can access the same memory module at the same point of time. So here, in order to restrict the access of multiple CPUs to the same memory module at the same point of time, the priorities are assigned to the CPUs. So memory module can be said to have four ports, and each port accommodate one of the buses. Assigning, and you're going to assign fixed priorities to each memory port to resolve the memory access conflict. So here, priority established for memory access associated with each processor by the physical port position. So if you take the CPU1, the CPU1 will have a higher priority than CPU2. The CPU2 has a higher priority than CPU3. The CPU3 has a higher priority than CPU4. So if CPU2 and CPU3 try to access the main memory module 1 at the same point of time, in order to resolve the conflict, whichever is having a high priority CPU, that is allowed to access that particular memory module. This is how the conflicts are resolved in case of a multi-port memory. So coming to the advantages, the high data transfer rate can be achieved because of multiple paths. And disadvantages, it requires expensive memory control logic to be implemented in order to check the priorities. And a large number of cables and connections are required. Good for a systems with a small number of processors. So the next type of an interconnection structure is a crossbar switch. So the crossbar switch, it contains a number of cross points that are kept at the intersection among the memory module and the processor bus. So, in each cross point, there will be a small square that represents a switch, which obtains path from a processor to a memory module. And each switch point has a control logic to set up the transfer path among the memory and the processor. So, if you consider here the same thing, so here Between the CPU and the memory module, this particular connection is established by means of a crossbar switch. So these are all the different crossbar switch that connects the memory module to the corresponding CPU. So whenever a CPU wants to access a memory module, say CPU 1 wants to access the memory module 4. So it will put its request onto the corresponding. Whenever this memory module receives this particular request from CPU 1, it checks whether this particular request is to that particular module. If this is not to that particular module, then it will just forward the request to the next memory module. So similarly, the next memory module also checks and it forwards it to the next module. Like that, whenever request is received to the memory module 1, when it identifies that it is to that particular module, it will be accessed by the particular CPU. So this is how a crossbar switch works. So coming to the advantages and disadvantages of a crossbar switch, it supports simultaneous transfers from all the memory modules because there are separate paths associated with each module. So from each CPU to each memory module, it goes through a separate path. So it supports simultaneous transfer, which is the advantage of the crossbar switch. Coming to the disadvantages, the hardware which is required to implement the switch is quite large and complex. So these are the disadvantages. Coming to the next type of an interconnection structure, which is a multi-stage switching network. So the basic component of a multi-stage switching network is a interchange switch, which is a two input and two output switch. So if you consider this is an example of an interstage switch which contains two inputs A and B and two outputs 0 and 1. So if you see this diagram, in the first one, A is connected to the output 0. So this particular switch allows the input to be connected to any one of the output. It contains internal control signals that allows to connect the input to any one of the output. So A is connected to 0 in this case. In this case, A is connected to 1. In this case, B is connected to 0. So here B is connected to 1. So based on this interchange switch, using this particular 2 by 2 switch, you can eh, as a building block, it is possible for us to build a multi-stage network to control the communication between multiple sources and destinations. So in order to see how this can be done, you can implement it using either a binary tree with a 2 by 2 switch or 8 by 8 omega switching network. If you consider binary tree with 2 by 2 switch, all these are the 2 by 2 switches and from a particular source to destination. Say for example, this is a processor and there are multiple destinations like memory modules, say, or multiple processors like P0, P1, P2, P3. So in order to allow a processor to connect to other processor which is present in the network, you can implement the concept of this 2 by 2 switches. So if you see here, it starts from the processors starts from 000 to 111. P0, P1, P2, P3, P4, P5, P6, P7. So overall there are 8 processors connected in the network, and from any processor you can connect to any other processor present in the network with the help of this particular switch. So if you see 000 from this particular processor, the output is 0. It goes through this particular output 0 and 0. So it is so this binary number 000 is allocated to this particular processor. So similarly, if you look at 101, so 1 0 output and 1 101. This is how this processor can connect with any memory module or any other processor which is present in the network. So the same way you can also implement a switch using an 8 by 8 omega switching network where you have 8 inputs and 8 outputs, 0 to 7 and here 0 to 7. So using multiple switches present internally in the network, you can connect multiple sources to multiple destinations using an 8 by 8 omega switching network. So the next type of a interconnection structure is a hypercube system. So you can call this hypercube system also as a binary n-cube multiprocessor structure. It is a loosely coupled system composes of 2 to the power of n processors interconnected in a n-dimensional binary cube in the form of a binary cube. So here 2 to the power of n means that if you take the value of n as 1, 2 to the power of 1 means there are two processors which are connected in the particular system, and each processor which acts as a node of a particular cube. And similarly, if you consider 2 to the power of n as 2, 2 to the power of 2, so you have 4 nodes or 4 processors connected to the particular cube structure. And if you have n value as 3, you will have 2 to the power of 3, 8 processors or 8 nodes which are connected by means of a binary cube. So here each node or a processor assigned a binary address, and this address will be assigned in such a way that the address of two neighbors differ exactly with one bit position. So for example, if you consider this particular hypercube system, this is for one cube where your value of n is 1. So to the power of 1, you have only two nodes 0 and 1. So if you take this is a 2 cube 2 to the power of 2 where you have 4 nodes 0, 0, 0, 1, 1, 0 and 1, 1. Through these 4 nodes you have created a cube. Similarly, 2 to the power of 3 you have 8 nodes which are connected by means of a cube, 3 cube. So if you consider the addresses of these particular nodes, they are assigned the addresses in such a way that the neighboring nodes differ by exactly by one bit position. So for example, if you see this particular node 0, 0, 0, if you look at its neighbors, this neighbor has 1, 0, 0. There is a difference with only one digit, this one. So this neighbor 0, 1, 0. There is a difference with only this particular digit. So if you look at this particular neighbor 0, 0, 0, 0, 0, 1, there is a difference with only one particular bit. So all the neighboring nodes are assigned, addresses are assigned in such a way that the address of two neighbors differ exactly with one bit position. And here the routing of the messages also takes place. So whenever a message has to be routed from one end to the other end, how the routing can be done? So routing the messages through an n-cube structure, it may take from 1 to n links from source to destination. It can be a one link or n number of links to move to move from source to destination node. So in a 3-cube structure, a routing procedure is designed by determining the exclusive OR of the source node address with the destination node address. And the resulting binary value will have 1 bits corresponding to the axis on which the two nodes differ. So the message will be transmitted along a particular axis. So if you consider example, a message at a node 010 going to node 001. So if you consider this particular example, a message from 010 it has to go to 001. In this case, how the message can be routed? So you have to take an exclusive OR of 010 and 001. So if you consider an exclusive OR of 010 and 001, it produces an output of 011. So this is x-axis, this is y-axis, and this is z-axis. So wherever you get ones, so you are getting one on y-axis and z-axis. So the message has to be transmitted along the second axis, y-axis, to the node 000. So from 010 along the y-axis, it will transmit and it will reach 000. From here, since z-axis is 1, it will transmit from 000 to through z-axis, it will reach 001. So you have to perform an exclusive OR of the two addresses, which will be equal to some particular result. From the result, whichever axis is 1, in that particular direction, the routing will be done. This is how hypercube system works. Thank you.